All right, let's pick up where we left off last time. We were talking about classifying our benzene ring as being an aromatic compound. And we had these two rules that we laid out for aromaticity here. And last class, we really just kind of focused on that first one, but now let's incorporate the second one as well, okay? So we have these two rules that will make a compound aromatic. First, they have to be a fully conjugated ring, which meant that all atoms had to have that sp2 hybridization, okay? Remember that if an atom has that sp2 hybridization, that means that all atoms in that ring have these balloon-like orbitals, these peanut-shaped orbitals. And if they're all sp2 hybridized, then you got a bunch of these peanut-shaped orbitals all in a row, and the electrons can move themselves between these orbitals, okay? They don't stay put between just two, they spread themselves out across all of those orbitals, okay? This is a phenomenon we call delocalization, right? Delocalization meaning that they don't stay put. Localized would mean like stationary. Delocalized means they're moving around, all right? So we said that we have to have a fully conjugated ring and that we have to have an odd number of those delocalized electron pairs in that ring, all right? So again, what do we mean by delocalized? These are not stationary. But spread out across multiple orbitals. All right, this was a pretty profound thing that was discovered. I had said benzene plays kind of this outsized role in organic chemistry. All right, this idea that you have these orbitals and these electrons spreading themselves out, that was a really radical idea about like 100 years ago, because up until that point they had imagined that electrons were a lot like little marbles, basically, right? Like little solid sphere particles that you have. But in fact, quantum mechanics came along and was like, actually what we should be doing to better describe these electrons is to start talking about them as waves. And all of a sudden the organic chemists were like, oh crap, that fits in perfectly with what we've been seeing in our data, because those electrons, they just must not be staying put, but spreading themselves out, right? Long waves spreading themselves out across all of these orbitals, delocalizing. Okay, and so kind of the weird criteria is we have to have a specific number of electron pairs in order to be considered aromatic, and that is an odd number of those delocalized pairs, okay? So importantly, when we're talking about our delocalized electron pairs, which one of our bonds here in this ring are going to be delocalized? These ones here. And we got a fancy term for these type of bonds. What are that? What's that? Pi bonds, all right? So when we're counting our delocalized electron pairs, we're counting pi bonds. And we're gonna add to this list here in a minute. I'll complicate things. All right, but for right now, we're just gonna deal with counting pi bonds. Okay, so if we've been paying attention, we kind of know the punchline here. Benzene is indeed an aromatic compound, but let's just convince ourselves that it follows those two rules here. Okay, do we have a fully conjugated ring? What we need to do is make sure that all atoms in this ring are sp2 hybridized. So we're gonna say, all right, this one is on either side of this double bond, on either side of a double bond, on either side of a double bond. Great, I made my way all the way around the ring. I have a fully conjugated ring, all right? And then we gotta count electron pairs. Again, delocalized electron pairs. So how many pi bonds do we have? 1, 2, 3, is that an odd number? Check, check, right? So benzene satisfies both of these rules here, which is why we would classify benzene as an aromatic compound. All right, so I'm going to lay down a bunch of different molecules, and we're going to go through and we're going to classify them as being aromatic or not aromatic. We may or may not have some fancy terminology for not aromatic. All right. going to attempt the most difficult of all the polygon shapes here, a 7-sided ring. All right, we got these 5 molecules. We're going to classify them as if whether or not, depending on whether or not they follow our 2 rules here. Okay, so you can take a minute to copy those down. Okay, and then actually take a minute to see if you can't go through. See if you can't apply those 2 rules. Does it satisfy rule 1? If so, move on. Does it satisfy rule 2? All right, so do we have a fully conjugated ring here? All right, so we're going to go through and we're going to highlight all of our sp2 hybridized atoms, the ones on either side of our double bonds. But then we get to this one. This is not an sp2 hybridized carbon. It's not a part of a double bond. And so this thing right here messes up our ring's conjugation, okay? And we had a special term for these molecules that fail rule 1, right? So again, we're applying these rules to see if these compounds are aromatic. This particular compound fails rule 1. Meaning it is non-aromatic. So conjugated means that every single carbon, or every single atom, is sp2 hybridized. And the reason that that's important is because then it has that little balloon that sticks above and below the plane of that molecule. Just like when we talked about pi bonds for our alkenes, we talked about how they have these orbitals that stick up above and below that bond. Benzene is a compound where every single carbon in that ring is shaped like that. right? And if it has that little balloon that sticks up and below, that allows the electrons to delocalize across that entire ring. If one of those carbons does not have a balloon, then all of a sudden the electrons, they can spread themselves out over here, but they can't make it the full way around the ring, okay? So that's why our first rule is we need a fully conjugated ring, meaning all those atoms are sp2 hybridized. This one is not a fully conjugated ring. We got this one in the middle here that's sp3 hybridized, and so if it fails that first rule, we call those compounds non-aromatic. All right, over here, our little square. Do we have a fully conjugated ring?
Yes.
Cool, all right. So this and this, these are part of that double bond, so they're sp2 hybridized. This one and this one are on either side of that double bond, so they're sp2 hybridized. That's all of our carbons. We got a fully conjugated ring. Cool, so now we'll move on to rule 2, which is to count the number of delocalized electron pairs in this molecule. We have 1, 2 of our pi bonds. So does this satisfy rule 2 or fail rule 2? Fail, right? This is an even number of electron pairs. All right, so just like we have a special term for molecules that fail rule 1, we got a special term for molecules that fail rule 2. These are what are called anti-aromatic compounds. All right, we'll talk a little bit more about that in a second. For right now, we're just going to worry about classifying these, okay? So that was kind of the name of the game. I'm going to give you a molecule. You're going to classify it as being either aromatic, it follows those 2 rules, non-aromatic because it fails the first one, or anti-aromatic because it passes the first one but then fails the second one. All right, this thing looks kind of weird. All right, we got these fused ring structure. This molecule right here, fun fact, this is naphthalene. This is like the active ingredient in mothballs, which is not something that's terribly widely used before. But it's got that very mothball smell to it, which sometimes can remind us of our grandparents, for those of us that are older. All right, anyways. Yes, so widely used compound, not so much anymore. It is great to use in the lab as a quintessential, let's see if it's aromatic or non-aromatic. We're just going to play our same game where we go around the ring and say, are you sp2 hybridized or not? These 2 are on either side of a double bond. Whoa. These 2 are on either side of a double bond. All right. The ones in the middle, they're part of this fused ring, but they are still sp2 hybridized. These ones over here. These ones over here. All right. So if we trust the process and we just go around, we see that all of our carbons in this ring are indeed sp2 hybridized. So we do have a fully conjugated ring here. If we go through and count the number of electron pairs, delocalized electron pairs, we have 1, 2, 3, 4, 5. So does this satisfy rule 2?
Yes.
Cool, so then we would classify this compound as aromatic. All right, so these are our 3 terms that we're going to try to use here: aromatic, non-aromatic, and anti-aromatic. All right, see if you can apply that to this last. If you can do the last 2, that'd be great. We did talk about these carbocations last class. We'll go and review that again. But just see if you can't, for this triangle here, classify it as being non-aromatic, anti-aromatic, or aromatic. Okay, what do we got? Non-aromatic. Okay, so these 2 are sp2 hybridized, but this one is not a part of a double bond. That one messes up that ring's conjugation. Okay, and importantly, we laid out those 2 rules in order, right? You got to apply rule 1, and then if it passes, you move on to rule 2. But if it doesn't, you're done there, right? So all we're going to do is stop here and say, all right, this compound is non-aromatic. All right, if we look at our other triangle here, now the only difference is I made that top carbon into a carbocation. So when we go through and we say, is this ring fully conjugated? Well, these two are sp2 hybridized, and exactly what we reminded ourselves about carbocations are these carbocations are sp2 hybridized. So carbocations are sp2. Oh my gosh. Okay, meaning they do not mess up our conjugation. Okay, so now I need to go through and I need to count the number of delocalized electrons. I passed rule 1, right? So I'm going to move on to rule 2. I'm going to count the number of delocalized electron pairs here. Okay, I have my 1 pi bond, and importantly, that carbocation, it doesn't mess up the ring's conjugation, but it also isn't bringing any electrons to the game here, right? It has an empty p orbital that can accept electrons from these full p orbitals over here, but it itself doesn't have any electrons to bring to the game. So when I'm totaling up my number of electron pairs, there is one electron pair in this ring. All right, so let's just make note here. Our carbocations are sp2 hybridized, meaning that they do not mess up our conjugation. They also do not contain electrons. So with my 1 electron pair here, what would we classify this molecule as? Aromatic. Cool. All right, awesome. So again, we're going to classify compounds as aromatic, anti-aromatic, and non-aromatic depending on our 2 rules that we apply. All right, we can just say if it fails rule 1, we call that non-aromatic. If it passes 1, but then we move on to 2, we call that anti-aromatic. And it fails, rather, we call that anti-aromatic. Okay. All right, so let's just take a second and talk about these 3 terms here: aromatic, non-aromatic, and anti-aromatic. All right, so for the purposes of this course, we're going to kind of simplify things in terms of what we need to know for these terms here. We're not going to do any like molecular orbital theory or anything like that. That would really help kind of deep dive and explain these. So what we need to know about compounds that are aromatic is, again, they follow those 2 rules that we laid out, and they are super stable. All right, compared to like what you would expect in your theory calculations based on similar molecules, it turns out that when you link all those double bonds together in a ring and it meets that criteria of having an odd number of electron pairs, all of a sudden something happens to the free energy of that compound where it's just super duper stable. Okay? It has to do with what we talked about last class about being able to draw these resonance structures, being able to draw these electrons moving in multiple positions. Any molecule that has that is just got this extra stability in the energy world. And it's like your natural next question is why? And we're going to have to blame it on the quantum mechanics gods for that one, right? Super duper complicated physics question at that point. All right, non-aromatic compounds. These are average stability. So these ones are just like exactly what you would expect based on your theoretical calculations. If you took a straight chain alkene, it would have the same energy as if you linked it up into a ring if it didn't have that fully conjugated network, right? Nothing different about the straight chain in the ring if we're comparing two non-aromatic compounds. And then anti-aromatic, kind of as the name implies, is bad, all right? Anti-aromatic compounds are super unstable. It is oftentimes difficult to even get those compounds to form, even to get that ring linked up to make that anti-aromatic compound. Because there's something about that even number of electron pairs that just makes that compound way higher in energy than what you would expect. All right? So this is sort of the breakdown of what we have to do as to why those compounds are just super unstable. Is a very complicated explanation involving the molecular orbitals that these electrons form. All right, so this is just a fun fact here. It turns out that when you take those 6p orbitals, they mix themselves together to form what are called molecular orbitals, where those electrons live. You start out with 6 individual atomic orbitals, and now you have 6 new molecular orbitals. 3 of them are really good, 3 of them are really bad, and it turns out with an anti-aromatic compound, you end up having unpaired electrons in your molecular orbitals. And electrons don't like to be unpaired. And it's like, wow, thank you for that really complicated explanation. It didn't really solve much, but yes, that's what it has to do with. It has to do with these molecular orbitals that these electrons live in. Cool. This is what we need to know. All right. What we need to know is aromatic, really good. Non-aromatic, meh. And then anti-aromatic, really bad. Okay? Cool. All right, so now we're going to complicate things a little bit by talking about what are called heterocyclic compounds. All right, where our goal is to do the same thing, to classify them as being either aromatic, non-aromatic, or anti-aromatic. But what I mean by heterocyclic compounds is that they have one of those heteroatoms, which remember is just a term that we mean is anything other than carbon and hydrogen. Yes, anything other than carbon and hydrogen. So what we're going to see now are these rings that, for example, contain a nitrogen in the middle of the ring instead of a carbon atom. So we still have a bunch of pi bonds here, but now we have this heteroatom in this ring as well. All right, so let's take a look at 2 examples. Again, going to attempt the impossible 7-sided polygon here. I even worked with a protein for like 4 years that was a 7-membered ring, and we would draw these little heptagons to represent it, and I still can't freaking get it down, all right? It's just the weirdest of all the shapes to have to draw. All right, so heterocyclic compounds, again, we mean compounds where carbon is replaced by another element in our ring. All right, and really the key here is that we're going to have to take a look at these lone pairs that are on that ring. All right, so that's going to be kind of the new thing that we're introducing to our set of rules here, is we have these atoms that have these lone pairs. Okay? And again, our goal is to classify as aromatic, non-aromatic, or anti-aromatic. Okay. And we're going to do the same thing. We're going to apply those same two rules. All right, so we need a fully conjugated ring. And we need that odd number of electron pairs. Delocalized electron pairs. All right, so let's go up here. We need to see if we have a fully conjugated ring. All right, so 4 of these are really easy to tell. We're just going to do the exact same thing that we've been doing. These ones are on either side of a double bond. These ones are on either side of a double bond. All right, but then we get to our heteroatom here. And the question is, what do we do? All right, is this nitrogen right here sp2 hybridized or not? Okay, and what happens is this nitrogen, it gets to choose. It gets to choose whether or not it's going to be sp2 hybridized, and then it will contribute to that ring, or it's going to be sp3 hybridized, and it's just going to bow out of the ring altogether. All right, so these heteroatoms, they get to choose whether or not they're going to be sp2 hybridized. All right, so how do they make this decision then? Well, they're going to be sp2 hybridized if adding that pair of electrons to the ring makes it aromatic. All right, the decision is whether or not nitrogen is going to put that pair of electrons into one of those peanut-shaped orbitals so that it can play with the other electrons in this ring. And it's only going to do it if doing so would make that ring aromatic. All right, if not, it's just going to be sp3 hybridized and the compound will be non-aromatic. All right, so we say that our heteroatoms get to choose. So yes, if those lone pair electrons make the compound aromatic. All right, so I'm going to go around and I'm going to see if adding that pair of electrons would make that compound aromatic. All right, I'm going to count my number of delocalized electron pairs. 1, 2. But if nitrogen puts that pair of electrons into that ring, that would make a total of 3. All right, so if that lone pair gets added to the ring, is this compound going to be aromatic or non-aromatic? Aromatic, right? So indeed, that nitrogen is going to be like, all right, great. Then I'm going to be sp2 hybridized like everybody else in this ring, and that will make our compound nice and stable and aromatic. Okay? So the question is whether or not you count that lone pair of electrons, or rather, if you count that lone pair of electrons, does it make that ring aromatic? Does it give it that odd number of electron pairs?
Would each lone pair count as one, or is just in that case just one over?
A lone pair is one pair of electrons, right? And that's what we're counting here, is delocalized electron pairs. Cool? All right, so I want you to do the same thing with this compound here, but I'm going to tell you right now, oxygen's got 2 lone pairs. It can't possibly put both of them into that same peanut-shaped orbital. There's only one peanut-shaped orbital available. It can't put both lone pairs in there. So one of these lone pairs is off limits. It's definitely not going to be participating in the conjugation of the ring. So only one lone pair can delocalize. All right, so take a second and see if you can't classify this compound here based on what we've discussed about our rules of aromaticity. All right, so do we have a fully conjugated ring? We're like, all right, everything's going easy. Cool. Oh crap, what do we do with this one? All right, and again, in order to answer whether or not this thing is going to be sp2 hybridized, we got to see what that lone pair wants to do. Does it want to join the ring because that would make the compound aromatic, or is it going to stay out of it because it doesn't want to make the ring anti-aromatic? All right, so we got to count our number of electron pairs. We have 1, 2, 3, and if I count this lone pair here, that would make 4. So do I want to count the lone pair? No. All right, so to be clear, what's going to happen is this oxygen is then going to be sp3 hybridized. It's not going to put that lone pair into the ring if it makes it anti-aromatic. So it's just going to change its hybridization so that lone pair is sticking out away from the ring. And if that oxygen is sp3 hybridized, what would we classify this compound as? Non-aromatic. All right, so this first example was aromatic. This one is non-aromatic.
So then with these, will you never have an anti-aromatic?
Exactly, right? You'll never have a heterocyclic atom that's anti-aromatic. Instead, they just won't put that pair of electrons into the ring. They'll point it out elsewhere, right? I mean, like physically in space, what this oxygen atom is doing, let me just get rid of all my coloring here to make a point. It is having one pair of electrons sticking out in this direction and the other sticking out in that direction, pointed out away from that ring. Whereas what the nitrogen is doing over here is making itself look like one of these little balloons. Whoops. It's putting its lone pair of electrons into a little balloon so that they can spread itself out across the ring with all the other electrons, right? So it's changing its hybridization depending on whether that ring would be aromatic or anti-aromatic. Okay, so our heterocyclic compounds here, we have two examples of an aromatic compound where that lone pair will join the ring, or a non-aromatic compound where that atom's going to be sp3 hybridized instead. Okay, cool. So now the last thing that I can ask you about here would be the number of localized versus delocalized electron pairs. All right, so what do we mean by delocalized? Right? These are the ones that are participating in that ring's conjugation. Okay, so these are either going to be pi bonds, or we saw with our heterocyclic compounds examples of delocalized lone pairs. All right, so then what do I mean by localized? These are electrons that are not spreading themselves out across the ring, right? They're going to stay stationary. So these are not conjugated. Okay? And these could also either be pi bond electrons, pi bonds, or lone pairs. All right, so we got to look at our molecule and see whether the electrons in those bonds or lone pairs, if they're spreading themselves out or not. Okay, so let's take some examples. Actually, real quick, let's just focus. We've talked quite a bit about delocalized, rather. Let's just do some examples of some localized. All right, so if we just had a regular old alcohol group, that oxygen's got some lone pairs on it, but those lone pairs aren't moving around at all. They're just chilling right on that oxygen atom, right? So this would be our normal old alcohols here. Both of those lone pairs would be considered localized. If we had a so that would be a localized lone pair, to be clear. If we had a normal old alkene with just a one single pi bond here, that pi bond pair of electrons right there is stuck right there. It's not moving around that molecule at all like we've been seeing. So that would also be localized. Okay. Just one thing to clarify here. If we want to do a delocalized example. We've been looking at ring structures, okay? Let's say that I take a molecule and I give it two double bonds. If I look, all of these atoms have that sp2 hybridization, right? So if I imagine, I'm going to attempt this here. Let's see how this goes. If I imagine those balloon-like orbitals here, here's my one pi bond where that pair of electrons is being shared. But now I have this neighboring molecule that has that same exact geometry with its pi bond. And again, since I have all these p orbitals all lined up in a row here, these electrons will also spread themselves out. Okay? This compound is not aromatic because it's not a ring, but it still contains delocalized electrons. Anytime we have those sp2 hybridized carbons all in a line like that, those electrons are going to spread themselves out. Okay? So these are delocalized. Let me actually use a different color. These bonds right here would be considered delocalized. All right, because of that geometry, these electrons can spread themselves out across all of those orbitals. Cool. All right, so let's just take our previous examples that we went through and kind of count our number of delocalized versus localized electron pairs here. All right. Let's actually start with some of our easier ones. Let's take these two. All right, so just take a second and total up, count the number of localized pi and lone pair electrons and delocalized pi and lone pair electrons. Okay, so this one we said was aromatic because all of these carbons had that sp2 hybridization. And then when we counted up our number of delocalized electron pairs to determine whether this was aromatic or non-aromatic, we said there were 1, 2, 3, 4, 5, that odd number. So if I'm asking you for the number of delocalized pi bond or lone pairs, there would be 5 of them, right? And how many of those pi bonds are localized? None, right? And I don't have any lone pairs here, so I don't have any localized electrons. Okay. What about my square here? We did our fully conjugated ring. And we said that there were 1, 2 delocalized pairs, which is why this was bad and anti-aromatic, right? So if I'm asking you to total up the number of delocalized electron pairs, there are 2 of them. And how many localized electron pairs do we see here? None. Cool. All right. Let's do this guy here. 5-membered ring. All right, and I guess I just will put up here. We had said this one was anti-aromatic. One was aromatic. And this one, oh, I guess I'm giving it away. Okay, tell me whether this is aromatic, anti-aromatic, or non-aromatic, and then total up the number of localized and delocalized pi bond and lone pairs. All right, what is this compound? Non-aromatic, anti-aromatic, or aromatic? Non, right? We got our 1, 2, 3, 4 sp2 hybridized carbons, and then this one right here messes everything up. Okay? How many delocalized electron pairs do we have in this ring? We still have 2, okay? Because these 2 double bonds here have that perfect spacing where they're all going to have that sp2 conjugate hybridization, we do still have 2 delocalized electron pairs, okay? So just make note, even if you're anti-aromatic or non-aromatic, you can still have delocalized electron pairs. right? You just don't have that extra added stability of being classified as aromatic. Cool. All right. So then what about if I take my 5-membered ring here? All right. But I'm going to replace that carbon at the top with an oxygen atom. All right, I want you to take a second, play the same game. Classify it as aromatic, anti-aromatic, non-aromatic, and then total up the number of those electrons that are localized and delocalized. And to be clear, whenever I'm asking you to total these up, I'm talking again about pi bond electrons and lone pair electrons. There's a bunch of sigma bond electrons in there as well. All those single bonds, I'm not talking about those. Without a lone pair. Yeah, you could make a carbanion that had a lone pair as well, but it would have to have a lone pair in that ring, yep. All right, so what do we think? Who says this compound's non-aromatic? Who thinks it's aromatic? Wonderful, awesome. Okay, cool, we get the name of the game here. So we're going to look, we're going to say, all right, all of these are sp2 hybridized, and then I got to ask whether or not this oxygen's going to participate in the ring, right? It gets to choose whether or not it's going to put this lone pair into that ring, and it's only going to do it if it makes that ring aromatic. So now I got to move on to my next step where I start counting. I have 1, 2, and if that oxygen joins the party here, now we have 3. So indeed, it's going to go ahead and make itself sp2 hybridized, and this compound would be aromatic. So then how many delocalized electron pairs do I have? All those that I counted, right? Including that lone pair. So I could be even more specific. I have 2 delocalized pi bonds and 1 delocalized lone pair. Do I have any localized pi bond or lone pair electrons? Yes, right? And with oxygen, you will always have at least 1 because you can't possibly have both lone pairs delocalized, right? Oxygen can only have 1 of those p orbitals. So yes, now I have 1 localized, and I can even say it's a lone pair. All right, for the sake of going through a ton of examples here, let's do one more. And we'll go to that another one that we sort of looked at earlier. I lied. We're going to do 2 more and stack them next to each other. Our triangle without the positive charge and our triangle with the positive charge. All right, so same game. Anti-aromatic, non-aromatic, or aromatic, and then number of lone pair and pi bond electrons. Cool. All right, so for this first one, what would we classify it as?
Non-aromatic.
Non-aromatic. All right, we have this guy right here that breaks that ring's conjugation, so we don't have a fully conjugated ring. If we go to this one here, we're going to say these two are definitely sp2 hybridized, but also remember that carbocations are sp2 hybridized, and this would have an odd number of delocalized electron pairs, so this one would be aromatic, all right, with one delocalized pair of electrons and no localized pair of electrons, okay? Now, what about if I asked you localized versus delocalized electrons on this molecule here, okay? Does this molecule have any delocalized electron pairs? All right, so it's got a pi bond for sure, right? But remember, a pi bond is only able to be classified as delocalized if it has that neighboring pair of p orbitals that it can travel into. Regular old alkenes that don't have the ability to spread themselves out are just localized pi bonds. So in this case here, without that additional atom that it can move over to, this would just be considered a localized pi bond. So one, and that's our pi bond. Nothing is delocalized in this molecule. This is just a regular old alkene. All right, so just to be clear, if we want to compare that to our other non-aromatic compound that we looked at, we said that this one did have delocalized electron pairs, but again, that's because it's got two sets of pi bonds in a row, so those electrons can spread themselves out to those positions. All right, so just to make note of these two comparisons stacked next to each other. Cool. All right, so that's going to be a big part of this particular chapter is this classification here and counting of electrons. All right, what I'm going to kind of introduce and what we're going to spend next week on exclusively are the reactions of these benzene derivatives. All right, so let's take two similar molecules here. Let me grab a good structure. All right, so the first functional group that we introduced, right, we talked about alkanes and how they were kind of boring, and then we introduced our first exciting functional group, I should say, the alkenes. And we learned about a bunch of reactions of alkenes, all right, but they all sort of looked the same. They were all the same class of reaction, all right? Does anybody remember what that class was?
Addition.
An addition reaction, right? So alkenes, they undergo what are called addition reactions. So if, for example, we took our halogen, we're just going to leave it as X, that would get added to that ring, right? Where I would replace my pi bond in my ring with one of those new single bonds on either side. Okay, cool. So, let me just, for the sake of comparison here, move if we do the same thing with benzene here, you look at benzene and you're like, all right, benzene's got a bunch of double bonds, right? So let's look and see if we did this exact same reaction. Okay. We break that pi bond and we create these two new single bonds. Okay. The top reaction we know happens, right? We've said that these are addition reactions of our alkenes. If we look down at the bottom here, I'm going to tell you this reaction does not occur. All right, why is that? Why is there something bad about the product compared to our reactant? Benzene we would classify as what? Aromatic, non-aromatic, anti-aromatic. Aromatic. And what about my product over here? What would I classify that as? Aromatic, non-aromatic, or anti-aromatic? Non-aromatic, right? So in order for benzene to undergo an addition reaction, it would have to go from that super stable, low energy aromatic to a meh stable non-aromatic compound. Compounds don't like going from low energy to high energy. That's not how reactions happen, right? They go the other way. So we're not going to do these addition reactions. Benzene, we're going to say, does not undergo addition reactions. Okay. Instead, we're going to introduce a new class of reactions here, what are called substitution reactions. Okay. So what we're going to see is instead, you can actually react benzene with a halogen. All right, but what we're going to get as our product is one of these hydrogens on this benzene ring. And this is going to be really important to keep in mind when we start looking at these substitution reactions next week, is we don't really draw that implicit hydrogen in there. I'm going to draw it in to make a point. But you have to sort of remember that in these reactions, we're swapping a hydrogen for a new atom here, for a new bond. All right, and so that's exactly what's going to happen here. We're going to replace that hydrogen with a halogen. All right, so in a substitution reaction, we substitute out or replace that hydrogen for a new bond. All right, and we're going to cover a few different substitution reactions. Okay, we'll learn about a few different things that we can do to this benzene ring. All right, to be clear, one big mistake that people make is they say, oh, X2, boom, X2 here. Now all of a sudden you're breaking the octet rule of that atom, right? So for those of you that are sticklers for your balanced chemical equation, we can note that the other product here would be HX, right? We got to account for all atoms. But again, in organic chemistry, we get lazy. And so you will often see this without that inorganic product written, right? Typically speaking, all we're doing is showing what's happening to the carbon. We're not writing a balanced chemical equation. We just care about our organic product. So if you look through your textbook, you'll see, I don't know if ever it mentions the fact that you have this here because it's not worried about balancing a chemical equation. But you can note that that is where that other halogen goes. Okay? For getting into our particular reactions, I don't want to do that. I don't want to rush through that with 10 minutes left. All right? So what we're going to do is we're going to save our electrophilic aromatic substitution reactions. These substitution reactions we're going to talk about, we'll save that for next week, all right? And that'll be a big focus of next week. I'm going to have to rearrange some of your homework assignments But basically, I'm going to have to take one away. So, anyways, I'll postpone that until next week. And yeah, we'll get into these specific substitution reactions next class period.
Are we still gonna be able to do the end of week assignment?
I'm going to have to take a few problems out.
Okay. You send an announcement when you
I will,
get that.
yep.
Thank you.
Cool. All right, y'all. Enjoy your weekend.
Have a good week.